Hello people, welcome to Gurukula. I am Jai. I am working for R.M.K College of Engineering and Technology under the Department of Electronics and Communication Engineering. So today in this video we are going to see about a special topic that is what we call it as Hamming code, which is an error correction code. So error correction codes are basically will have the capability of detecting an error and as well as to self correct the errors that has been occurred in the sequence of data that has been transmitted. So in this video we will be talking about how Hamming code exactly works and how does it corrects the error that is occurred in the stream of bits that have been transmitted. So now without any further ado, let's get into the topic. So in the past few videos we were discussing the various sets of codes which are used for error detection and then error correction, especially by the data link layer. So as far as error detection codes are concerned, we might have discussed three codes. The first one is parity bits, second one is checksum, and third one is cyclic redundancy check. So all these codes are capable of only detecting the errors. So it will just tell you whether if there is any occurrence of error in the received stream of data or not. So now we will just put a little step ahead and then we will see something called as error correction codes. And under error correction codes there are several types of codes that are available, but here in our course we are going to discuss a type of code, we call it as Hamming code. And your Hamming code is capable of detecting the error and as well as it will self correct the errors. So we will see Hamming code a little bit deeper into it. So Hamming code is what we call it as error correction codes, as we all know that. So Hamming codes are capable of detecting and as well as correcting the single bits errors. So what about the multiple bits error? There are multiple other different sets of codes that are available, and this video is just to tell you that how error correction codes are differed from the error detection codes. So just to tell you the thin difference between the error correction code and then the error detection code, we are going to take up a very small example that we are going to perform with the Hamming code is concerned. So basically Hamming code works on a very pure parity bit concept, but with a slight modification. We will see what that slight modification in a minute. So let us take an example and then we will understand the working of Hamming code here in this particular video. But before getting into the video, I wanted to put a disclaimer at this particular point that the complete theory of the Hamming code is not going to be discussed in this video, as it is out of scope for this lecture series. So this video will only cover the working of a Hamming code so as to understand how exactly the errors are corrected with respect to communication networks is concerned. So we are going to see only the thin difference between the error correction codes and then the error detection codes, and the complete Hamming code is not going to be detailed intensively in this particular video. So with this disclaimer point, let us jump into the topic. So before getting into Hamming code, we have to have a structured way of Hamming code. So what is that particular structure? Why do we need a structure for a Hamming code? Is all because so Hamming code is a slightly different than previously discussed error detection codes. So how is it different? In all the previously discussed error detection codes, we have studied about the concept that if this is the stream of data which I am going to transmit, there will be a part of data bits which I wanted to transmit, and then there will be a group of bits, we call it as redundancy bits. So these two things will be totally called as the code word, and this is what will be transferred from transmitter to the receiver or source to destination, whatever it is. So and these redundancy bits will be removed at the receiver side, and then these bits will help us to understand if there is any occurrences of errors in the data stream or not. So this is what a general bird's eye outline of all the error detection codes that we have seen so far. Now we may have a question that what if this particular redundancy bit have experienced an error? So in that particular case, then the system may not be able to detect if there is any error that is occurred on the data stream or not. So that is the reason there is a slight modification in the structure of putting data bit and then the redundancy bit here in the Hamming code is concerned. So what makes the difference here? Instead of adding the redundancy bit at one corner of the data, what we are going to do is we are going to stuff the redundancy bit So since we are going to use the parity concept, I can call it as parity bit over here as well. So wherever I mean the parity bit, it is nothing but the redundancy bit. So not to get confused. Alright. So our parity bits are going to get stuffed within the data bits itself. So what am I trying to mean is, we are not going to use this particular format, which is I have a data bit and then my redundancy bit will not be in one particular corner. We are not going to use this particular format, but whereas in Hamming code is concerned, there will be lots of data bits I may have any number of data bits, but parity bits will appear in between the data bits. So forget about the number, I am just purely putting it for an example sake, and as you could see over here, I am going to put my parity bit. P represents the parity bit and D represents the data bit. As you can see, the parity bits are stuffed inside the data bits. Correct. So that is the key difference which we are first of all going to follow in the Hamming code structure. So altogether we are going to have two parts of bits in our total data stream is concerned. The first one is data bits and another one is parity bits. So when it comes for a system, everything is an algorithm and then everything is an protocol based. So it must be clearly defined that where am I going to put my data bit and where am I going to put the parity bit. Clear? So now it is time to define the positions of the data bit and then the parity bit. So let us take for an example, I have let's take 7 positions I have. So 1, 2, 3, 4, 5, 6 and 7. So let me consider this is the first position, second position, third, fourth, fifth, sixth and then 7th. So now these are all the positions. Now I must be very clear that, or I should say my system or my algorithm, that in which positions the parity bits are placed and in which positions the data bits are placed. So parity bits are always placed in the positions of 2 power n, where n runs from 0, 1, 2 and etc. So if n is equals to 0, so it is 2 power 0, it will be 1. And when n is equals to 1, it will be 2 power 1, which is again 2. When n is equals to 2, it is 2 power 2, that is 4 and so on. So we can clearly see that I am going to place my parity bits wherever I have 2 power n position. So first position, second position, fourth position, 8th position, 16th position and so on. So for an example concern, the first position I will be placing my parity bit, I will represent that as P. Second position is also allocated for parity and fourth position is allocated for parity as of this example is concerned. And the remaining places will be filled with the data bits over here. So that is how I can put my data bits and then the parity bits and then I can stuff these two bits together. So understanding the positions of data bit and then the parity bit is a very important step in proceeding with the Hamming code, and this structure has to be followed throughout the transmitting and then the receiving algorithm. So once if you are clear with this particular point, it's good to go for the next step. So now let us take an example and then we will try to understand how exactly the transmitter side algorithms will work. So for that, what I will do is I will take an example that I am going to take a data which is of 4-bit length. So 1101 is what I wanted to transmit from one point to another point. So let me take a same 7 position example over here. So 1, 2, 3, 4, 5, 6 and 7. So I have first position, second position, third, fourth, fifth, sixth and seventh. So we very well know that I am going to put my parity bit in 2 power 0 position, which is first one, 2 power 1 position, which is 2, and then 2 power 2 position, which is 4. And in remaining places I can put my data bits like this. So in order to differentiate, what I will do is I will just give a number that I am going to represent this as P1, P2, D3, P4, D5, D6 and D7. So now it will be very clear for us. Now what I will have to do is I will have to put my data bit in this particular positions. So again I have 7 positions. 7 position. So 1, 2, 3, 4, 5, 6 and 7. I very well know the data bits. So data bits are 1101. So I will put, so here is what my parity bit is going to appear, and here is what my second parity bit will appear, and in the fourth position I will have a parity bit. So remaining 4 bits I can happily allocate it for the data bits. So 1101 is what my data, and I have allocated in the respective data bits position. Now I will have to calculate the parity bit for this particular value. So when it comes to parity, we will have to decide whether am I going to follow an even bit parity or I am going to follow odd parity system. So here, as of our example is concerned, we are going to follow even parity system. So we are going to follow even parity system over here. So now we are supposed to calculate the values of P1, P2 and then P4. So let us see how to calculate these values. So P1, it is as simple. So what I will have to do is, I will have to take one value and then I have to drop one value starting from P1. So let me make it very clear. What I have to do is, I will have to take one position and then I will have to drop one position to calculate P1. So I will have to take the first value starting from P1. So position P1 will be considered, and then I will have to drop one position. So the second position will has to be dropped. So P2 will be dropped. I will have to consider the third position. So third position, what do I have in third position? D3. So D3 I have in third position. So fourth position, it will be dropped. I will have to consider the fifth position. I have D5. Sixth will be dropped. Seventh has to be considered. So I have D7. So if I replace the values of all the P and D over here, I will get the parity value. So initially I wanted to calculate the parity bit value, and we can very well see that this parity value is dependent on the D3, D5 and then D7. So what is D3? So D3 is 1, D5 is 0 and then D7 is 1. So we very well said that I am going to use an even parity system. So even parity system represents that including the parity bit, the total number of ones must be even in number. So already we have even number of ones here in the data bits itself. So the parity will take a value of 0. So that is how I will have to calculate the P1. So how do I calculate P2? It is as simple as that. You will have to take two values and you will have to drop two positions. So two positions you have to consider, two positions you will have to drop. So what are the two positions? Starting from P2. Fine. So I will start from P2. If I start from P2, the immediate second position is D3. So D3 I will consider, and then I will have to leave two positions. So fourth position and fifth positions I will leave, and then I will take next two positions. So D6 and then D7 I will consider. So D6 and then D7. So now I can calculate the values of P2. So P2 value will be dependent on D3, D6 and D7. Right. So what is the value of P2 which I am going to calculate now, and what will be the values of D3, D6 and then D7? So it is all ones. So 1, 1 and 1. So now I am following even parity system, but I have odd number of ones in the data bit. So in order to make it even, my parity bit should be 1 over here. So the value of P2 is 1. So how do I calculate P4? P4 is also of same technique. I am going to take 4 values and I am going to drop 4 values. So that is the technique for calculating P4. So starting from P4, I will have to take 4 values or 4 positions. So P4, D5, D6 and D7. So these are all the 4 positions which I have to consider. There is nothing to leave after D7, so that we need not consider that particular part. So P4 is the value which I wanted to calculate, and what is D5? And D5 is 0, D6 is 1, D7 is also 1. So I have even number of ones in the data bit, so the parity bit will take the value of 0. So now I got the values of P1, P2 and then P4. Now let us see what will be the code word which I will have to transmit from transmitter side to the receiver side. So I have 7 positions, 1, 2, 3, 4, 5, 6 and 7. So this is the first position, second position, third, fourth, fifth, sixth and seventh. And we very well know that I have a data bits in these positions. And then now I will have to fill the parity bits whatever I have calculated in the previous calculations. So parity bit P4 is what I calculated as 0, and then P2, that is what I calculated as 1, and P1 I have calculated that as 0. Now this entire stream of data is what we call it as code word. So this code word is going to be transmitted from transmitter side to the receiver side. So this is what actually happens at the transmitter side, and you can very well see that this stream of data, you can see that the parity bit is actually stuffed inside the data bit. It is not actually present at one corner. It is not present at either in this corner or in this particular corner. You can see that the parity bit is evenly distributed among the data bits also, so that I can say that the parity bits and then the data bits are mixed up together. But only the algorithm knows that in which positions the parity bits are there and in which positions the data bits are there. So this is what will be happening at the transmitter side. So now let us see how this particular code will be received and processed at the receiver side. So as far as the first case is concerned, what I am going to do is I am not going to consider any error side. So I am not going to consider any error. So I am going to consider the data as such. So what I have received over here is, so let me rewrite the 7 positions, 1, 2, 3, 4, 5, 6 and 7. This is 1, 2, 3, 4, 5, 6 and 7. So what is the bit which I actually received? It is 1, 1, 0, 0, 1, 1, 0. So this is what actually been transmitted, and I have not introduced any error. I am considering the bits is received as such. So here I will have to calculate P1 again. So what is P1? So P1 is nothing but it is an data bit value of, you will have to consider P1, and then P1 will be dependent on the data bits like D3, D5 and then D7, which is what we have written in the previous slide. So now replacing the values of P1, D3, D5 and D7, what do I get? I will get 0, 1, 0, 1, correct? So now again assign a parity value for this, even parity value for this. I totally have 2 number of 1s, so that the new P1 value is also going to be 0 over here, correct? So now similarly calculate P2. We very well know that P2 will be dependent on the data bits D3, D6 and D7. So replacing the values of these values, what do I get? I will get all ones. So totally I am using even parity system. I have 4 number of ones. So the newly calculated P2 is also 0. So similarly calculate P4. Your P4 will be dependent on the data bits position D5, D6 and D7. So I can replace the values of all these P and D values. I will get 0, 0, 1, 1. So that assigning an even parity system for this, already I have even number of ones. So I will be assigning 0 for this. So when you encounter all zeros, then that represents there is exactly no error in the received bit. So that is how the sequence of values will be processed at the receiver side is concerned. So now what we will do is we will try to include some error over here. So where do we include some particular error? We will try to change this particular bit. The 5th position is on error now. So if 5th position is on error, what do we have? Instead of 0, we will have 1. Correct. So this is what the error which we have manually introduced over here, just to check how error correction is happening. Correct. So we will see how the receiver side will function if there is any error. So what I will do is I will actually rewrite the positions. So 1, 2, 3, 4, 5, 6 and 7. So this is 1, 2, 3, 4, 5, 6 and 7. So now the received value is with error. So I will write 1, 1, 1. 0, 1, 1, 0. So now this is what the received value, and we now manually we know that the 5th position is on error. Now let us see how the algorithm identifies that the 5th position is on error. So similarly the receiving algorithm has to be initiated. First of all I will have to calculate P1. So P1 is nothing but it is the position of P1, D3, D5 and D7. So replacing the values of P and D, I will get 0, 1, 1 and 1. So there are odd number of ones over here. So the newly calculated parity value should be 1 in order to make it even. correct? Fine. So now simply calculate P2. So P2 will be dependent on P2 and then D3, D6 and D7. So replacing the values of P and D bits, I will get 1, 1, 1, 1, and then already there are even number of ones present, so that I can happily assign 0 for this. The newly calculated P2 value is 0, and similarly calculate P4, and P4 is dependent on P4, D5, D6 and D7. So now replacing the values of P and D, I will get 0, 1, 1 and 1. I have odd number of ones here, so that in order to make it even, the newly calculated P1 value will be, P4 value will be 1 over here. So now I can see that there is a non-zero value occurred over here. So the first inference what I got is I have received a non-zero value. So non-zero value represents that the received bit is on error. So there is some error that have been occurred in the transmission stream. So that is the first inference my system will get. So now this we are talking about error correction codes. So my error correction code simply should not tell me that there is an error in the received bit, it should also correct it automatically. Fine. So how does it corrects? In order to correct it automatically, my system should know where exactly the error have been occurred. Correct. So that should be the second thing which has to be addressed. So where exactly the error have been addressed? So put the values in the reverse order like this. So you will have to replace P4, P2 and then P1 in this order, replacing the values of P4, P2 and then P1. So this is what the binary value. Converting this to decimal value, you very well get that it is 5. So converting this to decimal value, you will get 5. So that represents that position. So position number 5 is on error. So what is on position number 5? On position number 5 we already have 0, and if 0 is to be, on position number 5 we have 1. So if 1 is an erroneous value, then what we have to do, we will have to complement this particular value so that it will be automatically corrected to 0. So 0 is the correct value over here. So this is how the error correction code will automatically correct the errors that has been received at the receiver side. So this is how a simple basic Hamming code will work, and then this is how the errors will be corrected automatically there at the receiver side. And then more advanced code like cyclic codes and then trellis code, turbo codes, all these codes are available for the extensive error correction mechanisms, and all the introductions of these codes will falls on the digital communication part. Since it is an out of scope for this lecture series, we are just taking up a very light content of the Hamming code is concerned. So this is all about which you wanted to understand about the Hamming code, and then you can just feel that how the error correction codes will actually correct the errors at the receiver side is concerned. So that is all about today's particular video, and then I hope you will be understanding how this Hamming code is exactly working, and then how the error correction is happening at the receiver side. So I'm going to wind up this particular video at this point, and then I'm going to see you in the next video. Until then, it's bye from Jay and happy learning.